This is part two of our Centroid talk. So we kind of left off here last time where we had done a composite centroid, just two simple rectangular shapes, so nothing super complicated. But if you didn't watch that one, then you probably should go watch it first. Otherwise, it's going to kind of look like we're jumping into the middle of centroids. We're going to carry on with this with a little bit more complex part, so still a composite shape. And then we'll do one that has a centroid that uses some pre-built shapes, like pre-built I-beam type shapes. And those are the two main things we'll do today. Most of what we'll do will be working with this composite shape. So let's create a new shape that's a little more complicated, has a couple of new features that we have to keep track of, and we'll use our chart, one of these type charts here. A lot of these you can just type in Centroid chart into search engine, and you will get all sorts of these things. You do have to be careful. There are very similar diagrams that look like this, but they're actually giving you moment of inertia, or sometimes it'll be called second moment of area. And it looks very similar. Sometimes you'll even get combined charts that have centroids and moments of inertia on the same chart. So you just have to make sure you're getting the right kind of chart, but they're all pretty much the same. You're looking for a chart that has triangles, some kind of circular sections, some parabolas maybe. You don't really, we're not going to really deal anything with these arcs. So this would be as if you took a wire and made this shape versus having the solid shapes here. So we just need these. A lot of them aren't going to have circles, and they aren't going to have rectangles because the centroid of those is intuitive. It's just in the center. So it's going to have the ones that we'll need. This chart will. Other charts, here's another version. Same thing, but this one does have some rectangles on it. It doesn't have circles still, but it'll have different centroids. So there's all sorts of these. Just search for one that you like and find that one. Here's the shape that we're going to deal with. First, we need a coordinate system for it. So I've lost my ruler. There it is. We'll try and make this one neat. Let's see. Let's straighten up my paper, though. There we go. There's our y-axis. So I'm going to predetermine where the x and y axes are. And obviously, wherever you put the x and y axis in relation to your part affects the measurement of, the actual number that you would have for the centroid location. So you do have to pay attention to that. I'm just going to go ahead and put it out here kind of in the middle of the page. So there's X. This one we're going to use an arc, or well, not an arc, but a semicircle. So let's get our circles over here. Use one of the bigger ones. Maybe, well, if I can get it to line up, maybe that one. So only half, though. We use something like that. And then we will make a base across here. So this centroid is not necessarily going to be the cross section of a beam necessarily. You don't have to only calculate cross sections of beams. You can just have the centroid be the centroid of a shape, a 2D shape. And so that's more what we're doing here, is not necessarily the cross section of a beam, but a shape. So I'm going to put a triangle on this end. And then we're going to punch a hole in the middle of this thing somewhere over here. All right, so there's our generic shape. It's got a triangle, a rectangle, a semicircle, and a circle, with the circle being a punched out, a hole in the thing. So we need to get some dimensions on here so that we can define it better. We'll use this. Let's say that we need to know where our triangle is. Actually, let's drop these down a little bit because we're going to have to put some dimensions inside of here. And then here's our semicircle. I didn't really draw exactly, where it's at, but we'll kind of define it here. Okay. We'll get a dimension all the way across here. This triangle will have that dimension. this rectangle will have whatever that is. So for the triangle, let's give it a dimension of 3. So 3 inches or whatever. Let's give the rectangle, if this is 3, then this looks like maybe almost 6, maybe 5. Let's give a height here. We'll put it over on this left-hand side. So these little lines I'm drawing right now, they're called leader lines when you're drafting or whatever. And so if you're actually drafting the part by hand, I don't know if people even still do that really, but if you are, then the leader line has kind of a gap, maybe a 1/8 inch gap between the part, which has these darker lines, and the leader line, which is going off to some dimension somewhere. So there's a little gap there. That way it's not confusing if that is part of the drawing or not. Normally when you're dimensioning a part, you don't put dimensions on the actual object. You put them out around it as much as you possibly can. This one, if this is 3, that looks maybe like it's 4. And I'm not putting units on these, so if I were drafting this, I would actually have a box somewhere over here that had the date it was made, who made it, the scale that it's at, and things like the units, maybe some other material properties or whatever, some other notes that would go with this drawing. So I'm not going to draw the box down here, but that's normally where the units would be. So the numbers would be all in the same unit system, and then the units would be shown somewhere down here. Let's see what else we need. We need to locate this circle, and we need to dimension it. We don't have a dimension. So when you're doing a circle, normally you have its center, which I didn't actually mark. So something like this. And then you point to the center with a leader line, something like this. And then you come off of that with the dimension. And you normally don't do this with a free-floating ruler. Normally you have a ruler that's in a certain horizontal position, so everything's parallel. But we're not being super picky with this. We're just kind of making it our way. So if this is 4, then that looks, I don't know, maybe it's 1 inch. It's probably a little more than that, and we'll say that's the diameter. Do we need? Oh, we need to know where this is also. So this one being on this side, I'm actually going to pull it off of this direction. Oops, missed. And then we'll measure down. You normally don't have an actual x-axis on your drawings either. We're going to put this right in the center of our part vertically. So if it has a 4-inch height, then this is 2 inches. And that also is going to center up this semicircle on the end. We just need this distance now. So I'm going to pull it down here and kind of nest it inside of this one. And let's see, if this is 5, that looks maybe like 4. That's similar to that. So we'll call that a 4. All right. For now, I think we've got everything dimensioned. If we need some more, we'll add them when we need them. All right. So what I normally do next, if I'm trying to calculate the centroid of this composite shape, is I identify the parts. So I do have a part that's a triangle here. I'll call that part 1. The rectangle here, part 2. The semicircle on the end, part 3. And then the hole in the middle, I'll call that part 4. Okay. You could arrange, as long as you create the same effect, then it doesn't matter what parts you use. Maybe you want to, for some reason, make this triangle into 2 triangles, and that's okay. Maybe instead of having a rectangle plus a triangle to make this shape, you can build one big triangle and then subtract this triangle over here to make that shape. So either way is fine. There's always multiple ways. Well, always is a strong word. There are many times multiple ways to build the same shape with different parts. I don't think there's a simpler way to build this shape with parts that are made of triangles and semicircles and circles and rectangles, your basic parts. So I think this is probably the simplest way to break this down into primitive shapes. Then what I would do is I would go in and mark where I think the location of each part centroid is. So I might go in and say that the triangle centroid is somewhere over here. The rectangle is right in the center of it, so try to get somewhere right there. That circle, it is at its center. This semicircle over here is on this line, but it's pushed in a little bit, so somewhere right there. So I just mark them in roughly where I think they are, more as a aid to when I calculate numbers to see if those numbers make sense with what I think is going on. And remember, for each one of these shapes, the centroid is, if I took this shape and cut it out of a rigid material and tried to balance it on a point, that centroid would be the point that it would balance on. It's kind of balancing up here. And so I'm just kind of making guesses right here. And then I'm going to go in and actually use my charts to find where these individual centroids are, because our goal is to find the centroid of the composite shape, but you have to start with finding the centroid of the individual shapes. Remember, we're trying to solve the equation. Where's my pen? Here it is. Let's see, where do I want to put this? Maybe up here. Summation, well, x sub c equals summation of a times x over a, and y sub c equals summation of a times y over a. So those are the equations we're trying to solve. We're using the discrete method, not the integral method. It wouldn't really make sense to try and integrate this shape. So we're going to use a discrete method. And you could just plug numbers straight into the equations, and that would be completely legitimate. It's just harder for me to keep track of, have I accounted for all the numbers. So we're going to use a little chart down here like we did last time with the T, wherever I put it, over here. Like we did this, we're going to build one of these type charts, but for this shape. So the next step would be to go in and find where each of these centroids for this part is in reference to my coordinate system. So I have this coordinate system that I'm trying to measure everything from. So I don't know if I'll bother writing in the location of the rectangle. Maybe we will, because it's simple to do, but some of these, if they're obvious, maybe you don't take the time to write them down. We'll write them down because we're being thorough. So this one, I can actually just continue this line and say that those three centroids, the rectangle, the circle, and the half circle, we know they're all 2 inches from the bottom. Now this circle is 2 inches from the bottom because I put it there. These others are because the centroid is located halfway through their distance. So at the radius over here and halfway through the height there. Triangle is not that way. So let's pull it a little leader line off to the side here that we can dimension. If you don't remember, this is where the charts come in. So you grab one of the charts, maybe this one, and you got some triangles on it. And there's actually two. One of them looks like on this chart it was drawn after the fact, and then you've got one that's not a right angle chart triangle. We've got X bar. So in this chart, they're using X bar as X sub C and Y bar as Y sub C. Some of them actually say YC and XC and all that. This is the same thing. So this triangle is not exactly the same as our triangle. Our triangle looks like this. Their triangle is mirror image of that. So we do have to mentally, invert or flip this thing over to make sure that we're measuring the same thing. I mean, it'll be even more flipping when we have to deal with this guy because ours is turned that way. All right, but it looks like they've got right here this distance labeled as y bar, and they say y bar is equal to h over 3, and h is the height of the triangle. So unfortunately I made the height of the triangle 4 instead of like 3, so this is 4/3. So we have all of our y locations. Now we need all the x locations. So let's do the triangle again. Now you might remember we did the triangle by integration, and we came up with x sub c is 2/3 of the base. So this is why I draw things out. Oh, also when you have leader lines that line up, you normally do line them up. You don't kind of like offset them a little bit. If you offset them, you make a significant gap between them. So we'll line this one up here. So if you draw this and you've drawn things more or less to scale, then that distance does not look like 2/3 of the base, right? So you have to go back and say, well, why is that? And then you check your chart over here, and here they've got an x bar, and they've got it labeled as 1/3 of the base. So what's going on? So what you have to do is you have to match up the shape that you have and where these dimensions are being measured from and to. So here they're measuring from the right angle over to the centroid and saying that that is the base over 3, so 1/3 of the base. And that's what I labeled here because I want to measure from my y-axis. It's my reference point, so I want to measure from the y-axis over. So that's the right angle over to the centroid, 1/3 of the base. My base is 3, so this is 1. Oh, I don't like that I did those backwards. Messing up our picture. Okay, good enough. The other thing with this is that this isn't just 1. This is 1 in the negative x direction. So positive x is going to the right. From my y-axis, I have to go to the left to get to this centroid. So when I plug this into my chart, I need to be sure I put a -1 for the x coordinate of this guy's centroid. You could even go in, I don't normally do this, but you could go in and write the, the coordinates here, -1 4/3. Like it's a point in this coordinate system. So you could do that to keep track of that -1 if you wanted to. This guy, another way you could do it, I suppose if you take this same approach and not drawing lines on it, you could say, well, this is the centroid of the rectangle. The rectangle has a base of 5, so I know the centroid, without even looking, is 2.5, right in the middle of that. And then it had a height of 2. So we could label them that way. This one's already labeled, right? See, there's a 4 setting it over from the y-axis, and a 2 setting it up from the x-axis. So it already has coordinates, they're just over here. So it would be x of 4, y of 2. This one is a little trickier. So you're measuring from the y-axis, so it is 5, but then there's this little distance right here that it's not in the center of this thing, so we got to figure out that distance. So we go back to our chart, and here's a semicircle, and they do have that distance that we're interested in. It's right here, but they have it labeled as y bar, so you don't automatically just take x bar or y bar. You have to look at the distance that you're interested in right here, line it up with what they want. If you have to rotate or flip or rotate and flip or whatever the picture that they've drawn, you've got to do that mentally or maybe do it physically, like turn the paper sideways and see, I want the one that in this paper, in this chart, they're calling it y bar, even though I want something in the x direction. They're saying that y bar, this is it right here, 4r over 3 pi. So that r is talking about the radius of the circle. So 4r over 3 pi. And then I can go back to my diagram that I'm working with, and this distance from here, the base of the circle, to the centroid, that is what is 4r over 3 pi. We could calculate that, I suppose. 4 times the radius of this circle is 2. 4r over 3 pi is 0.849. But when I go to put this number, the centroid location, you know, create the little coordinate system for it, or the coordinate set, x is going to be 5 plus 8.49, so 5.849, and y is the 2 inches again. All right, I don't think we can do anything else here that's valuable, unless you want to go calculate the area of each part and write it on the chart. I think that would be a little bit overkill, so I'm not going to do that. And now we'll create our chart down here that has the shapes. And I normally, whoops, that's off our page. Let's zoom out. There we go. I normally go in and draw a little picture of the shapes and number them. So I had number 1 being a triangle, and I draw a little triangle for it. Number 2 was the rectangle, a little rectangle. Number 3 is the half circle. And number 4 is a hole, so I normally draw it with a little dotted line to remind myself that it's not there, it's a subtraction. So there's something, you know, you don't have to do this part, but you're just setting up the rows for each of the parts. Now we need the area of each part. So the area of the triangle is 3 times 4, but it's a triangle, so 6 square inches. The rectangle is 5 times 4, so 20. The half circle it has a radius of 2, so we could do pi r squared, I suppose, since we have the radius. Pi times 4, but that would be for a whole circle. We only have half a circle, so divided by 2. 6.28. This one is a cutout. It's cut away. Oh, I wanted to point that out also. A lot of people, when they get to this triangle, or this, not triangle, this rectangle, they want to put in the area the rectangle with the hole cut out of it. But what we're asking for here is the area of the rectangle, the solid rectangle. So that's why I did 5 times 4 is 20. Here's where we're going to take into account that there's a hole in the rectangle. So we're going to give this one a negative area because we've subtracted it. It's a hole punched through the rectangle. So it's a negative area, and the area has a 1 inch diameter, so it's just pi over 4. Right? Now, if we sum this total, that will be our total area that we want to put in our equation. So 26 plus 6.28 minus pi over 4. Oh, I put 6.23. Hold on. 6.28 minus pi over 4. 31.49. So that's the total area of the bracket, or whatever this thing is. That's the total area of it. Now we need, it might actually be good now to go in and look at this and try to kind of estimate where the centroid of the whole thing would be, just so that we can tell, you know, once we calculate it, if we're on the right track. So the 3 shapes over here, they all share a line here for where they're centered. The triangle's centroid is a little below that, so that should mean that the centroid for the whole thing is a little below this line. So these are all the same. This one's a little below it, so it's somewhere, you know, down in here. If I think about this thing trying to balance, I'm going to think it's, you know, it's clearly on this side. It's not trying to balance somewhere over here, but it's not just in the center of this distance, which would be, you know, right in here somewhere, because this triangle does pull that a little bit further. So I'm going to think that right in here is where the centroid of the whole thing is going to be. So when I calculate numbers, if that is in the ballpark, then I can be relatively certain that I've done the right kind of math. It's really easy to lose a negative sign in here. It's even easier to lose a negative sign when it's just in an equation all strung together. So I want to make an estimate take my calculations, compare that to my estimate, and see which one is if they agree, or if I made a mistake in my estimate or a mistake in my calculations. Let's do X. So this is the X coordinate of the centroid for each one of my pieces. So we could just go to our little ordered pairs here, and so that one's a -1. This one is a 2.5. This one is a 5.849. And this one is, we did write it down, it's 4. It's important to keep track of that -1 because that centroid from my reference point, which is the y-axis, if I'm measuring in the x direction, is in the -x direction. So need to have that negative sign. The y coordinates, 4/3 for part 1. These are all positive, so the x-axis is at the bottom, and I have to measure upwards to get to any of these. These are all 2, 2, 2, and 2, so that's easy. Now I want to do the summation of a times x, so every one of the areas times every one of the x's individually. A times x, that'll give me inches cubed. Again, it's not a volume, but it's square inches times inches. So this is 6 times -1. That negative is important, so this is -6. 20 times 2.5 is 50, right? Yes. 6.28 times 5.849. Oh wait, I did 628. All right, hold on. 6.28 times 5.849. 36.73. This one is negative pi over 4, so pi over 4 times 4. Well, I guess that's just pi, right? But it's negative. And this is the AX. We need to do the summation of AX. So we have -6 plus 50 plus 36.73 minus pi. 77.59. Okay, and we could go calculate this, but let's do the AYs and then we'll do the calculation. So area times y, 24/3, 40, 12.56, and pi squared over 4. And these are both, oh wait, I'm looking at the wrong thing. Pi over 2, negative pi over 2. And we sum this thing up. $58.99. I wish I had a little bit more room here, but maybe we can squeeze it in. XC is 77.59 over 31.49 2.46. Those would be inches. This is inches cubed. That's inches squared. So inches. So we thought that it was going to be just to the left of kind of the center of this side. 2.46 is, it's actually a little bit further left over here, but that's reasonable. We can believe that. So we thought it was over here. It actually looks like it's over here, assuming we did all our math right. We could have made a mistake in our math somewhere for sure, but I think we did it right. But so that doesn't alarm me anyway. It's not like 12.46 or something like that that really looks off. So, we're just making an estimate over here, and here we're doing an exact calculation. As long as they're reasonably close, I'm okay with that. YC is 0.99 over the same area, 31.49. 1.87. Same thing, it's inches because this is inches cubed, this is inches squared, so leftover units are inches. And that does look pretty much right. So looks like maybe we were just supposed to put this guy right over there. So we estimated a little bit wrong. Actually, it might be a little bit higher. I don't know. It's not important exactly where I draw the thing. It's, you know, these numbers that are what we're looking for. So the things to keep in mind on this one, it's not particularly more complex. It has more pieces to it, but the process doesn't actually change. But there are things you have to keep track of, like the negative areas or the negative coordinates of a individual piece if they're below the x-axis or below or to the left of the y-axis. And I think we did a decent job of keeping track of all of them. And generally, that's how you're going to work these composite shapes. Sometimes you might have a composite shape like this. So let's think about that T that we had before. And we built something like that. Maybe we handmade that or whatever, I don't know. But this is a beam now. This one, not necessarily a beam, but we needed to know the centroid for whatever calculation we were trying to do. Now we're back to thinking of a cross-section of a beam. And this beam just wasn't strong enough. So we took a store-bought beam and put it on top. Kind of like this, to reinforce our little T-beam that we had made. So let's give it a little bit different color so we can see it separate. So there's the store-bought beam, and we want to still find the centroid of this whole shape, but the store-bought beam is not like the same, like it's got these little tapers on the end here, and it's going to be difficult to go and measure all that, figure out its centroid, figure out its area. But since it's store-bought, then we can reference some charts that talk about these kind of beams. We just need to know the name of this beam. So what I have here is a chart for channel beams. Now these are shown, let's see if I can pull it down so you can see it. These are shown with the channel kind of pointing to the right, and we have the channel pointing upwards. But we can still use this chart. And you can look at the diagram in the top right corner, and it has a label. It's kind of small, but it has a label named X sub C. And in the far right column, there is a column of values for X sub C. So that is the location of the centroid for this channel. Now they've got it oriented in the X direction. We'll just call that Y sub C when we use it, but they've got that measurement already done. The second column has areas already calculated. We just need to know what's the name of the beam. So we're going to pick this beam, C9 by 20, and we will say that it has an area right here of 5.88 inches squared. So we've got that. And then X sub C way over here is 0.583. So I don't know if you can see those numbers close enough or not, but there's the C9 by 20. There's its area, 5.88, and then over here off the screen is its 0.583. And each one of these rows is a different size beam, and they have different names. We'll talk about the names in a second. So we just need to get this information right now. So we have this top piece, C9 by 20, and it has an area of, I think it was 5.88. Yes, 5.88 square inches. You do have to be careful with these charts because they do come in metric and in US units. So make sure you're using the one that you actually need to be using. And it has y sub c, or it's called x sub c in the chart because of the way they've drawn the diagram, but we've laid it down flat, and so it's y for us of 0. It's off the screen. 583 inches. All right. So now, if we put some dimensions on our T-beam, we know some stuff about the channel beam that we've welded to the top of it, then we should be able to calculate this just like a composite shape now. So we'll call the stem, remember this part is the stem, part 1, the flange part 2, and the channel part 3. And then let's put this at, let's just make it 1 inch. Let's make this height 4 inches, and let's make this thickness 1 inch. All right, and then we already have the dimensions for the channel on top. Need a darker pen. So we have 3 shapes. We have part 1, the stem, part 2, the flange, part 3, the channel. They each have an area. The area of part 1 is 4 times 1 is 4. Part 2 is 1 times, oh, I didn't dimension this length, but this is a good time to talk about this name. So this C9, the 9 is the nominal depth of the beam. Now, the depth of a channel beam is from this point to this point. So if we look at our chart again, and it is nominal. Now, in this case, they've got a column called depth up here. In this case, the C9 actually is 9 inches. And actually, all of the channels are exactly whatever their name are. That doesn't always work out with all beams. Like some beams could be a W10 and it's actually 9.5 inches tall or whatever, or deep. But that C9 is 9 inches in depth. And then for us, the depth is actually this width. And I drew it the same as the flange of the T that we made. So that kind of implies that the flange has a width of 9 inches. So 9 by 1 for the flange. The area of the channel is a piece of data from the chart, 5.88. And there's our total area. $18.88. This is another one of those that would benefit from having the y-axis right through the center of it. So the x sub c is just 0. And we'll have the x-axis going out that way. And we need to calculate all the y coordinates for the individual pieces. So part 1 is here, part 2 is here. Part 3 is one of those where it actually floats kind of in midair above the channel. So x, or no, this is y. Y for part 1 is the stem. It has a y of 2. I'm measuring everything from this bottom reference axis down here. So that's a 2. Part 3 is the middle, because it's a rectangle, middle of the flange, which is 4 plus a half. And then part 3 is we have to reference the data from the chart, 0.583 to get from the centroid to the bottom of the flange, and then I add 5 to that. 1 here and 4 there. So 5.583. And then I just do A times Y, 8, I don't know, 40 something, let's see, 9 times 4.5, 40.5. and then 5.88 times 5.583. 32.83. And there's my summation of A times Y. So 8 plus 40.5 plus 32.83 is 81.33. And Y sub C is equal to 81.33 inches cubed divided by 18.88 inches squared. 4.31. And then when we look at that on our chart up here, or our diagram up here, that would put it, 4.31 would be right in, actually there's 0.5, so it's going to be right in there somewhere. So that makes sense. Normally the centroid for a T-beam is, somewhere just beneath this junction between the flange and the stem. But we slapped on this channel beam, which pulled that centroid up higher, and now it's kind of in the middle of the flange somewhere, and that makes sense. This number seems reasonable. And well, let's go back before we quit. Let's talk a little bit more about this name over here. So the C, most of these beam names start with a letter, and so C is a channel. And it generally looks like a channel. Actually, there's two N's in channel. So it looks like the letter C, which is where its name comes from. A W beam doesn't look like the letter W. That W normally refers to wide flange. So remember, the flange is this part across the top. So wide flanged, and then it's normally an I-beam. So W normally looks like, maybe I'll write them over here, an I, but the flanges are kind of wide. There's an S, that's a standard flange, I-beam. So it has the same general I shape, but the flanges are narrower. There's a WT, which would be a wide flange T-beam. So capital letter T, but the flanges are kind of wide on it. I think there's an L that looks like the capital letter L, and it's a right angle beam. So there's several of these. That letter is talking about the shape of the beam. This first number is talking about the depth of the beam. Now you might think of depth as height normally, but it's called the depth of the beam. And so in this case, this would be a beam that's nominally 9 inches tall. Assuming you're in the US system, if you have a C9 something in the metric system, then that's 9 millimeters, and so it's a much smaller beam. But this is normally talking about the depth of the beam, or how tall it is. And the 20, or the last number, is talking about how beefy it is. So this is 20 pounds per foot. So if I cut off a foot-long section of this channel beam, it would weigh 20 pounds. And so this name gives you a lot of information about it, but normally you have to go to the charts and get the specific information. Like, for instance, like this 9 is normally 9.25 or 8.75, it's something around 9. It's not always exactly 9, although the channels that we have in this chart I'm looking at, the 9 is always 9 inches deep, and the 10 is always 10 inches deep, and so forth. So this name, we'll get, once we start dealing more with beams, which is coming up soon, this name will, we'll be more and more familiar with it. So I wanted to go ahead and introduce it now so that you had a glimpse of it, and how you might get some of the data from them, and we'll use some more of that later on. But I think that gets us through all the information we need for centroid calculations. If you have any questions, let me know. I see something now. Let's see. Oh, wait, I zoomed out. All right. Uh-oh. I did the area of the circle wrong. Let's check. because it is possible that I did the area of the circle wrong. I did the area circle here. I said the radius was 4. Oh, I did, didn't I? No. Well, I didn't mean to say the radius was 4. The radius of this circle, the half circle, is 2. The diameter is 4. And then I put in pi. I don't know what I put in. This is actually this area is the area of this one. So the area here, I put in 6.28. I don't even know what that means. So let's see. Pi d squared over 4. So I might have put a pi 2. Let's see. Pi times d squared, which is 4. So that would actually be 16, which I don't remember doing, over 4. And then we take half of that. Oh, no. Somehow we ended up, I think, correct. So I don't know what I said, but I think we actually did do it right if we're talking about this area. This area is the area of the circle here, which has a 1-inch diameter, pi d squared. So that's just 1 squared, pi over 4, pi d squared over 4. So I think that one's right also. I think they're correct, but there could still be problems. These numbers do seem reasonable, though. So I don't know. I'll have to check more carefully. That's the problem with doing these things live, is that I definitely could have multiplied something wrong. The general procedure is right, but I could have definitely multiplied something wrong somewhere. I'm not seeing it right now, though, but it is possible that it did. All right. And I generally, when I do these areas for circles, I generally use pi d squared over 4, but I could have used pi r squared also, since I had the radius. So let's see if that works also. Pi r squared is 4. And then I have to take 2. I think it's right. I don't know. I think it's right. I keep getting the right number. Either I'm doing the same thing wrong over and over again, which is also possible, or that number's right. Anyway, the process is correct. I might have an individual number somewhere wrong. That is always possible. Okay. I think we're good. I'll get back on Monday. If you're in the course on Moodle, there is an outline for the exam. It's called 2020 Exam 1 Outline or something like that. When you load it up, it actually shows a date like 2014. That's just because I use the same outline pretty much all the time. And I went back and used the 2014 one because it covers the same topics that we covered. So check that out if you want to see a list of the types of questions that are actually on Exam 1 and kind of their level of difficulty. All right. I'll be back on Monday.